So this is the group called the Boys, and here's our structural analysis of a light attack aircraft. You can see our SolidWorks model here of our wing. So let's begin. So for one, our aircraft in general, coming from the AIAA RFP, it needs to be designed to be affordable. It needs to be able to operate near the front lines, and it needs to provide close air support to ground forces on short notice. And to support these ground forces, it needs to be able to carry 3,000 pounds of armament, including missiles, bombs, and mounted guns on the aircraft somewhere. It will see 2 crew members, including a pilot and a weapons officer. So in terms of the structural analysis of it, we're going to be analyzing many different types of stresses, and you can see those listed below. The last bullet there lists all the stresses that we are analyzing in this presentation and report. And if you look at the figure on the right, this is our constraint analysis for our aircraft. We chose a single turboprop aircraft, and some of the constraints consist of 100 nautical mile cruise length, 4-hour loiter, different climb segments, and including 45 minutes of loiter time along with a reserve climb segment. And so by doing this constraint analysis, it's going to help us initially size the aircraft with relatively close lengths, which we will get into next. So using the design point that you saw on the last slide, it was around 60 uh, pounds per square foot and around zero point 0.1 to zero point 0.2 horsepower per pound. Um, so if this design point increases, that means the takeoff gross weight, as you can see on the table on the right, will also increase, and that increase in weight is going to lead to a bigger wing, bigger chord length, bigger span, and obviously bigger area. So it's important to get a design point that doesn't minimize the weight needed, but also doesn't maximize the weight required either. So you can see that our takeoff gross weight is right under 1,400 pounds, and almost 3,500 pounds of that total weight is going to be the fuel weight, which we incorporated into our structural analysis. Since the fuel is going to be located in the wings, we made sure to incorporate that in our analysis. And then also on the table on the right, you can see the chord length, the span, all the other details about the dimensions of the wings that are important to define the stresses, the strains, the shear flow. Uh, and that all comes together within the next couple of slides where we discuss those different types of stresses. One important thing is the fuel tank length. Since we are incorporating fuel into the wing, we had to calculate the fuel tank length, and that is assuming that the JP8 fuel density is 48.6 pounds per cubic foot. And JP8 is a military fuel that many modern military aircraft use today. So that was an important aspect. Just getting that fuel density really helped shape the size of the fuel tank.
So, starting with the structural configuration. First, the selection of the airfoil was determined by the RFP mission analysis proposed by AIAA. The airfoil coordinates for an EMB 314 Super Tucano were extrapolated to establish a base geometry. Next, the location of the stringers and spars needed to be determined. The logical choice was to start with the location of the spars, which theoretical data suggests that the front spar and the rear spar are normally located at 25 and 75% of the chord line. Once the spars were established, 10 stringers were spaced equidistant from the front and rear spar caps. This image on the right shows the location of each stringer and spar, as well as the CG, which was calculated using a summation of proposed areas and centroids. Before calculations were made, some assumptions needed to be made about the material. First, we assumed that it was isotropic and homogeneous. Second, it was also assumed that the analysis required on the wing was to be conducted inside of a wing box. This term means that the structural component of the wing that would be tested will be between the location of the two spars, thus forming something that somewhat looks like a box. So the first process to the in-depth analysis of the wing box was a flexural test of the wing. The bending stress was calculated using data obtained from the original design locations of the stringers and spars. From here, hand calculations and diagram labeling led to the analysis of a shear flow around the wing. This designates the points that were assumed during the shear flow analysis. Notice how the spar caps are treated as one stringer, going from 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8, all the way to the lower stringers on the bottom. This diagram represents the labeling of shear flow, and next, an allowable test was comprised of buckling, shear stress, and crippling stress that were conducted on the components comprised in the wing configuration. The analysis for this section could also be further categorized into primary and secondary buckling. The primary buckling dealt with the major dimensions of the structure, while the secondary buckling dealt with the cross-section dimension. A good way to think about this is that if your primary buckling fails, you have a big problem and you need to redesign. However, if your secondary buckling fails, it's okay, you can just fix it by a simple redistribution of the loads. Overall, there were 3 main tests for the wing structure. Bend it, break it, is it stable?
Let's talk more about the wing geometry. For the rib and the skin, we used a NACA 63415 airfoil shape, and the skin was 0.032 inches thick, while the rib sections were 1/4 inch thick. For the stringers, we used a Z shape, and the spar cap assemblies, we used a bracket shape, where the brackets faced the inboard rib section or the stringers. The stringers and spar cap assemblies were an 1/8 inch thick each. For the skin, we used a 7075 T6 aluminum, and for the other components, a 2024 T3 aluminum was used. The ribs were spaced 50 inches starting at the fuselage and working their way out, with the last rib spacing being 2.8 inches at the wingtips. There were 10 total stringers. They were placed equidistant apart between the rib, the spar and spar cap assemblies, and the positions measured from the leading edge are here. The stringers were placed above each other, so there are only 5 positions. Forward and aft spar cap assemblies were placed at these positions measured from the leading edge. And once again, the brackets were placed in to face the inboard rib section. There were 3 rib sections, the forward and aft, and then the midsection. Midsection was bracketed in order to house the spar caps as well as to house the stringers. The stringers, skin, and the rib will only be seen on the wetted wing section. This is 33.8 feet of the span, while the spar and spar cap assemblies travel the entire length of the span, 35.9 feet. The fuel tank was designed into the wing to be housed between the spar caps, spar cap assemblies, and it's 12.5 feet from the fuselage outboard. So starting at the midsection rib at the fuselage, 12.5 feet outboard on both sides.
The FAA discussion will consist of 3 main talking points: the loading conditions, which are the flight loads and fuel loads, the FAA model itself, and the post-processing and analysis. The flight loads were first modeled using a 2D airfoil CFD simulation to obtain the pressure distribution along the surface of the airfoil. This model is validated by comparing the airfoil characteristics to the published data, which match closely. Given the low case of flight design gross weight, lift, and drag loads were able to be calculated and applied to create a zero moment about the center of pressure. These were then applied as a uniform distributed load along the wetted span of each wing spar. The fuel loads were also numerically approximated, assuming that there were no volume losses due to the internal structure of the wing. The fuel weight distribution along the chord was approximated using the trapezoidal rule and then numerically integrated to find the CG of the fuel tank. At a low case of flight design gross weight, 60% fuel capacity was used, and they were applied to create a zero moment about the CG of the fuel tank. These were then applied as a uniform distributed load along the wing spars for the length of the wing tank, starting at the wing root and moving outboard. The FEA model consisted of two types of finite elements, 1D beams, which were the spar caps and stringers, and the 2D shell elements, which consisted of the rib web spars and stringers. The mesh was designed to maximize uniformity and compatibility between the structural members. Quadrilateral elements were chosen for the shells, and a maximum resolution of the mesh resolution of at least 1 square inch was guaranteed throughout the model. Boundary conditions, there was a fixed nodal translational constraint along the curves defining the wing roots, defining the wing skins and spars at the wing root, and the loads were applied as a total load along the wing spars. The first run of the analysis output a stress that was an order of magnitude higher than expected. Qualitatively, the stress distribution was consistent with that of a structure in bending. In order to determine whether this stress was an artifact or not, a gradient analysis was performed. For a linear static FEA model, outputted stresses should follow a linear pattern. However, as this plot shows, the stresses outputted for this model are highly nonlinear. In order to account for this artifact and compute the actual maximum stress at the wing root, the first step is to identify the region of initial linearity in the gradient plot. Then the next step is to perform a linear regression of this region and interpolate to calculate the maximum stress. In this case, at buttock line 30, which represents the wing root, the calculated stress is 55 KSI. This is below yield stress, however, but fails safety factor. Therefore, the structure was then adjusted, and this analysis was repeated until all structural members in the structure were under the limit stresses. The final design, the spark thickness increased initially from 1/8 of an inch to 3/8 of an inch. The skin thickness increased from 32 thousandths of an inch to 50 thousandths of an inch, and the skin changed to 7075 T6. Using 2024 T3, considering the stress limits, would create a burdensome thickness on the wing skins. The wing weight calculated was 636.14 pounds, and the limiting components were the stringers and compression, which had a minimum principal stress of 44 KSI, but with respect to the limit stress, has a margin of safety of 1.23. This stress was also far below the calculated stress required for buckling.
In conclusion, the goal of this report was to design the wing and conduct an in-depth stress analysis for an affordable light attack aircraft. For this, we chose a NACA 63-415 airfoil to construct the rib and the skin. The wing was 35.9 feet in span, and we used a bracket-shaped spar and spar cap assembly that were placed at roughly the quarter chord and the 3/4 chord. The stringers were placed equidistant between the spars. All in all, the wing structure was able to sustain all loads while maintaining a factor of safety. Because of this, there are no recommendations for change at this time. In the future, a more comprehensive model and analysis may yield results that require changes to be made, but at this time, the model is able to perform to the criteria assigned. And these are the references used for this report.